So we finished the orbital time scale climate change, and you got a bit more sense of the kind of feedbacks that exist in the system. So what we will do is now move into the glacial deglacial time, which brings us very close to the Holocene, and then in the next lectures we will move into the Holocene with more details, and then go to what is called millennial climate change, get to what is historical or since the Industrial Revolution, and then we will come back to global warming and recap most of the things, the kind of feedbacks, the future projections, what kind of feedbacks are important, and why we learned all these past climate changes, why we need to understand the climate sensitivity from the past to be able to see what the future brings, in addition to calibrating the models. Unless the models are able to reproduce some past observed climate change and climate variability, how can we be sure that their projection into the future is reliable? So this is one of the biggest exercises for the models, to be able to take tectonic forcing, as we saw some examples of moving the continents in Pangea and looking at super monsoon, or changing the orbital forcing and looking at what the response the model produces and whether that is consistent with the data, and what are the inconsistencies. If there are inconsistencies, is that related to inconsistencies or uncertainties in the forcing used for the model, and so on. So the deglacial timescale provides a very rich set of processes for the models as well, since we have much more data as we get closer and closer to the present time. So what is the deglacial time? Essentially, we go back to the end of the last ice age, which was around 20,000 years. So if you remember from the orbital forcing, in the last million years, we are in a 100,000 year cycle. So the last ice age started about 120,000 years ago and ended about 20,000 years ago, and we are technically in a deglacial period. What does that mean? Essentially, the extensive glaciers are not there. There is still glaciers on Antarctica, glaciers on Greenland and some mountains, but they are not there extensively on the continents like we have during the ice ages. So it ended last 20,000 years ago, and we are in the recovery from the last ice age. So what caused it? That's the first thing you have to figure out. And we know that the carbon dioxide at the end of the last glacial maximum was around 200 ppm. Pre-industrial level was about 280 ppm. We have been increasing it, and now we are over 400 ppm. So that increase started as the ice started melting. Remember, when glaciation happens, we said the atmospheric concentration drops by about 100 ppm. And when deglaciation happens, you will at least recover that 100 ppm back, and now we are adding other things because of agricultural lifestyle that started during the Holocene, which means we started clearing out forests and started planting crops, which would change the carbon balance and appear as increased concentration in the atmosphere. So we'll come back to that in more and more details as we go along. Okay, so here is the beginning of the melt of the large glaciers, increase of the CO2, and somewhat constant till then, but there are more details at the end that we will have to look at. How has the orbital forcing changed over the time? Remember, we need a trigger to end the glacial ice age, and on these time scales, typically it is the radiation change at 65° north or so. So at the end of the last glacial maximum, the summer radiation levels and the winter radiation levels were fairly close to the present, but the summer insolation started to increase and the winter insolation began to decrease. So the obliquity change gave us very large contrast between the seasons. But we know that it is the summer insolation that determines the melt of the snowfall from the previous winter, which can begin the melt of the glacier, retreat of the glacier, which would reduce the albedo, increase the amount of radiation absorbed by the system, which would further warm the temperature, and then you would get into deglaciation. So in fact, the summer insolation has now come back to the present level, and the winter insolation has come back to the present level. So the orbital forcing definitely helped start last deglaciation. The main thing then to see is if the deglaciation was continuous, if not, what internal feedbacks kicked in that created any kind of hiccups or jumps in the deglaciation. So, the ice obviously was 100%, which means compared to today we consider the last glacial maximum as 100%, and it decreased over time. As you can see, it was not really continuous. Then there are some very interesting feedbacks that we will look at. So, orbital forcing again has played a role in getting out of the last glacial maximum into the present. There have been enormous efforts since then, since this is the most interesting period, the last glacial deglacial transition, and since we have so many new geochemical methods that evolved in the last few decades, all the methods have been brought to bear on this problem to reconstruct as best as we can what the climate was, what the radiation was, what are the feedbacks that occurred, and how the changes have occurred over the time of the deglaciation. So, here is one of the first reconstruction. It is called CliMap, or Climate Mapping and Prediction. It was a large scale effort to take all the geochemical evidences like the sediment, ice cores, etc., and reconstruct the sea surface temperatures at the last glacial maximum. Okay, that's showing this. It's not very easy to see the difference unless you are very used to the current sea surface temperature map. In any case, to help you understand the differences, this lower map is showing the August difference in sea surface temperatures of the last glacial maximum compared to the present. So, you can see that the subtropical gyres were typically warmer than present, and the deep tropics was somewhat cooler, but North Atlantic especially was much cooler. You expect that because there were large glaciers. You would have affected the meridional overturning circulation or the thermohaline circulation. You also expect that it will have impact on higher latitude Pacific. The Indian Ocean, because of the monsoonal changes, also had some cooling, but the details are not always very certain, because even though this is mapped, the data you collect, remember the map of the ice cores and the sediment cores and the lake cores and tree rings and so on, that doesn't cover every point on the map. So, you take all the points you can get and you interpolate it as reliably as you can. So, we have to be aware that there is uncertainties here, but nonetheless there is more than 8 degree cooling that happened here, 6 to 8 degrees over there, and some temperatures were about 2 degrees warmer than the present. Why is that? Basically because if you cool higher latitudes and change the equator to pole temperature gradient, for example, you will change the circulation and you will change the Hadley cell. The strength of the Hadley cell would have changed. That would give you different temperatures in the subtropics versus higher latitudes versus tropics and so on. You would have changed the distribution of rainfall and so on as well. So, talking about rainfall changes, when glaciation happens, remember it produces, it grinds up things, makes the climate drier and makes the winds stronger. So, the fine dust, silt, etc., called loess, they get pushed and get deposited around the edge of the glacier. So, wherever the subsidence of the winds happens, like to the north of the Tibetan Plateau and so on. So, ice sheets and mountain glaciers eroded lots of debris of all sizes, and whatever is light enough to be carried by winds got carried and got deposited in both hemispheres. So, that gives you a sense of how extensive the glaciation was and that it was occurring in both hemispheres, not just the northern hemisphere. And this is showing now the sand dunes. There are right now active sand dunes in many places. That is related to how dry the climate is, how the winds are blowing, etc. So, if you compare the active sand dunes of today over Sahara's Middle East, the deserts of Afghanistan and northwest India and so on, to the sand dunes from the last glacial maximum, you can see the extent is much larger every place, especially here the Patagonian deserts and so on, and the Australian deserts. Remember, the continental configuration hasn't changed in the last 20,000 years. Everything is pretty much same, other than small changes that Australia is continuing to move north, India is continuing to push north, Himalayas are rising. So there are small changes. The drift of the African continent continues, but these are very small over 20,000 years. They are not responsible for these changes. These changes are purely related to glacial interglacial changes. So drier climate, more glacier volume produces more sand dune activity as well. So this is just a confirmation of what was happening during the last glacial maximum. So the other things that change, you have to remember again and again, when precipitation distributions change or the global climate gets warmer or drier, there is going to be vegetation response. Vegetation is going to change. Either it's going to change in latitude, warmer climates will make tropical species expand towards higher latitudes, or colder climates will make the forests climb down the mountains. If snow cover begins to, ice cover begins to build on the mountains, the forests will die and they will be pushed down, right? Same thing when lot of glaciers cover land like North America and Europe, Siberia and so on, that vegetation is going to change and move. So those are recorded in pollen. So the colder species like spruce, where obviously high, the pollen is recorded in sediment cores. You can look at the C14, remember the carbon 14 dating in lake sediments and so on, and we will see several locations where sediments are collected, and things like prairie grasses, which are warmer, drier species, appeared, and then the warmer species like oak pollen have increased over time as deglaciation became complete almost, and then the colder species disappeared from the latitudes where the glaciers retreated. So now it's too warm for these high latitude colder species around the latitudes of Minnesota, for example. We'll look at maps of these distributions in a minute, but you can see that the C14 ages are shown here. This is about 13,270 years, and this is very close to the present time. 1660 is the calendar year. So you can see that the cooling didn't happen continuously. We will see in more details why that is, and those are very interesting feedbacks that have great relevance for global warming. So here is a map of today's spruce pollen, and it's obviously observed in cold higher latitudes, relatively cold higher latitudes. There is a strong seasonal cycle, and the distribution during the glacial period, the glacier would have covered so much of the land that you would have pushed all the spruce further south. They cannot grow in the current climate here because it's too warm, but when you build glaciers here, you cool down here so much that spruce can grow at those lower latitudes. Okay, you have to remember that. And what is the difference between this and this? This is simulated, which means you take the same numerical model that we talked about, which is solving equations for momentum, energy, thermodynamics and so on, and you prescribe the past radiative forcing. So you reduce the amount of sunlight because of orbital changes, and you let it grow glaciers. So it grows glaciers that looks very similar. Sometimes you just prescribe it because some models may not have a glacier model in them, but you don't have to worry about those kinds of details. Nonetheless, it will have details of the vegetation, and you want to make sure that it is reproducing the response in vegetation that we can reconstruct from the data. This confirms that the model is able to reproduce one of the past climates, gives you confidence in the model. Once you have confidence, then you can reconstruct many things that are not possible from just the observations. For example, how the wind distribution changed. There is no easy way to reconstruct from any geochemical tracer how the tropical trade winds or the mid-latitude westerlies and the polar easterlies changed, how weak they got, how strong they got, or how much dust they were carrying, and so on and so forth. So, once you have a model that can reproduce the observed glacial distribution and vegetation change, then you look at all the details in the model, because the model is producing not just glaciers and vegetation, but it is also producing temperature change, humidity change, ocean circulation change, and the distribution of winds, which is very critical. So, you can fill in all the gaps that exist in the data by using the model once you are convinced by calibrating against observations that the model is doing proper simulation of the past climate. So, here is more example. This is the modern vegetation. There is little bit of ice now in the modern climate at high northern latitudes. There are Arctic forests. There are Mediterranean scrub. So, they are just different types of humidity levels, vegetation response by making use of the temperature and humidity and precipitation levels that are available. Okay. And there are deciduous forests, which means they drop leaves in cold climates, tundra and mountain ecosystems, and grasslands and steppes, coniferous forests, etc. So, we have for the modern time a great knowledge of how the vegetation is distributed. You can do it from satellites, from forest surveys, from aircrafts, drones, etc., etc., right. So, when we reconstruct glacial vegetation, we are relying often either on models or on pollen data from local lakes, river inputs, or local oceans, Mediterranean Sea, etc. And you can see again that the colder climates expanded the grassland and steppe into the higher latitudes because of the cold, dry climate, not enough humidity and not enough land. If this is under ice, obviously this will not grow. This was obviously all under ice, so that would not grow, but where there is land available, you will expand the drier vegetation because you have made the climate drier and cooler during glaciation. You have also made the land ahead of it cooler, so the cold vegetation would move down. So, you would get Arctic forest at such low latitudes over Portugal, Spain, and so on and so forth. Okay. These are very useful because we are now experiencing global warming where we are generally making lots of places warmer, but we will see when we do global warming that it is not like the entire globe is warming. Global warming means globally average temperature is warming, but this warming is not uniform. There are places where temperatures actually can get cooler for various internal feedback reasons that we will look at, and there are places which will warm faster, there will be places which warm slower. We will look at whether tropics warm faster or higher latitudes warm faster and why that happens and so on. So, in this case we want to be aware of two things: how will forests respond, plus remember we are relying a lot on agriculture now. So, we also want to be able to see what crops can still continue to be grown. If for example, a country like India gets really warm, whether the monsoon gets weak or strong, does it matter if temperatures get very warm? That is what we have to worry about, and how it changes with altitudes. Plus, there are strong associations between vegetations and things like mosquito populations, which means diseases like malaria, dengue, and so on. So, we also have to worry about so-called human ecology, in other words, how our own health depends on the change in ecology around us. So, all those details have to be figured out. In the past, obviously, we did not have very good data on what humanity existed, where they were colonized. More and more studies are now coming out to see how Homo sapiens began to move around. Neanderthals had disappeared by all accounts. Neanderthals had disappeared by about 25,000 years ago. So, if only modern human beings were around, where were they, at what latitude were they living, what diseases they were hosting, and so on. So, human ecology is basically understanding how our own health depends on the ecosystems around us. Another example, this is the glacially observed elm pollen, another vegetation that is very common to North America, and you can see here that observed pollen is only in the southern Gulf of Mexico region of the US. In case you are not aware, this is the map of eastern US, central eastern US. Here is Florida, here is New York, Maryland, DC, and so on. So, the Gulf of Mexico is here, and observed pollen records for elm show that it was prevalent here. When we simulate it with the model is producing slightly more wider and more intense distribution. So, there are two things. One, generally you assume that this means the model is doing fairly reasonable rendition of the past, but you also have to be careful to see if this difference is related to the fact that we cannot have very good data to map the past elm distribution as well as the model can do. So, there are many exercises involved in trying to understand what are the uncertainties in the data itself and what are the uncertainties in the model itself, so that you have a good idea of how much error is the model error and how much error is because we do not have enough data. This is always critical because even reconstructing from the 1800 to the present, for example, we do not have temperature distribution all over the globe from the past, from even 1800s. Lot of activity over Europe and North America where we have a lot of data, but all other regions of the world in Asia, South America, Africa, and so on, we may have no data. So, we always have to rely on a combination of data and models to be able to reconstruct the past and understand how to project uncertainties into the future. So, when you do future projections, you must always provide some estimate of how much uncertainty there is in those projections. We will see that when we come to global warming chapter. So, what was happening in the Antarctic? This is again the CliMap reconstruction, climate mapping and prediction project, and you can see that the winter ice in the modern times has some extent, and by all geochemical evidences we can estimate that the winter sea ice in the past was much more extensive. And you expect this. If you cool the northern hemisphere, that signal will affect the southern hemisphere as well, whether it is because of obliquity forcing or precession forcing or whatever. The two hemispheres communicate. There are many details as to how long it takes and whether they are always going in the same direction or not, depends on many things. Remember, for example, that obliquity will make the northern hemisphere have strong summer and strong winter, but it will also make the southern hemisphere have strong summer and strong winter. So, the glacier response depends on summer insolation. So, we have to kind of always track the hemispheric responses. In this case, the global glaciation, ice ages, both hemispheres have very cold temperatures. So, corresponding to the global cooler temperatures and northern hemisphere glaciation, southern hemisphere had much more extensive winter sea ice. Of course, we do not have very good data to say whether the glacier on Antarctica itself had thickened much more, but overall the ice cores that we looked at from Vostok and so on, they do show that there was much more cooling in Antarctica during that time, right. So, all the evidences kind of confirm the processes. What would happen in the tropics if you have glaciation at high latitudes? This is important because let us say we are interested in the monsoon. We are always interested in how the tropics respond to anything that happens anywhere, because that determines how the monsoon changes. And there is plenty of modeling and observational evidence to show that monsoon did respond to high latitude glaciation, and we will see how it responded. So, how will the tropics respond? If you have high latitude glaciation, then you will have regional cooling, but we are also during glaciation reducing the CO2 by about 100 ppm, and we are reducing methane as well by some parts per billion. That is not always well constrained. And solar radiation was similar during the last maximum ice cover as it is today. So, given the same level of energy, but reduced CO2 and methane, you expect that the tropics would have cooled. This already showed up in the map we looked at. So, you can see that the tropics generally had cooled. There is some little bit of warming here, about 0 to 2 degrees, but in general the tropics definitely were colder, which is consistent with what we expect in terms of a greenhouse response to glaciation. Okay? That would affect your land ocean contrasts and monsoons, but it would also affect the ocean circulation, where upwelling happens or how much nutrients are mixed into the surface layer where there is light, how much snow cover there was to even allow photosynthesis to happen, and so on and so forth. And these are the differences in glacial plankton versus plankton today. So, this is showing that in the North Atlantic, where there was extensive glaciation, the difference of plankton in the past compared to today was more than 50%, and there was also huge changes in the plankton here. Now, you have to go back and connect to the monsoon change we looked at with orbital forcing. We said there are, when the monsoon circulation here changes, there are upwelling changes here, and those leave biological signatures. Here we are going the other way. We are saying ice volume changes and high latitude cooling seems to have produced a plankton response, which means there was an upwelling response in the tropical oceans, which means there must have been a wind response as well, which means there must have been a monsoon response as well. This is true also for the Indian Ocean. Remember the southwesterly winds that come this way. If it is colder, that means you expect the winds to be stronger. But it gets much more complicated. Why? Because the moisture for the monsoon is coming from the ocean, right? If you cool the ocean, what happens to the amount of moisture that is coming in? Remember that warm temperatures hold more moisture. So, for the same strength of wind, if the air is warmer, you can evaporate more. But if you cool the sea surface temperatures, then you will reduce the evaporation. So, even if you made the wind stronger, were you bringing more moisture or less moisture? That is what you have to figure out. So, the net effect on the monsoon depends on how the radiation changed, how the ocean temperature and land temperatures changed, how the winds changed, how the sea surface temperature change and air temperature change affected evaporation. So, the moisture flux, for example, in a year in the monsoon season, India gets around 900 millimeters of rain. So, you can have the children take the area of India, compute how many liters or gallons of water falls if you distribute 900 millimeters over all of India. How much water is that? Most of the water has to come from the ocean, because there is some lakes and so on, and the rain that falls also can re-evaporate, but almost all the water has to come from the oceans. So, that will depend on all these kind of complicated factors. Nonetheless, going back to the plankton story, you can see that even the Pacific Ocean had very high rates of cooling in certain regions like the Gulf of Mexico or in the Tasman Sea or off of South America, Chilean coast and so on. So, this also begins to tell you that when you have radiative forcing and you have glacier growth, you are not producing a uniform cooling or a uniform warming. Remember the climate map of sea surface temperature change? This is the plankton map. So, you have to remember the sea surface temperature map. the cooling and the warming are not uniform, because winds change, upwelling changes, ocean circulation changes, amount of heat transported to be changes, hurricanes and cyclones also change. All together they determine where the warming happens, where the cooling happens, and that is very critical to see not only what is global temperature, but also what are the local impacts. That is always critical to understand local impact. So, all global warming is local. Nobody lives in global mean temperature, nobody lives in global mean sea level rise and so on. So, you have to always come back and project things into local processes and local impacts. That is always critical. But you know now that planktonic signature related to wind responses are recorded in each ocean. So, as we said, as the glaciation happens, the atmospheric temperature, remember we said if we look at height versus temperature, temperature is warmer near the surface and it decreases, right. There is a tropopause, and in the stratosphere is here where there is ozone formation, so temperatures warm again. This temperature profile or the gradient or in the troposphere changes when there is glaciation, which means as you go up the mountain, the top of the mountain is going to be cooler during the glaciation. So, during last glaciation, this is the example of Andes. The ice cover at the present time is above about 1000 meters, but during the last glacial maximum, the cooling came much further down by about a kilometer, and all the grasslands that now exist, if you go up in the Andes hiking, those also were pushed down, and so were the forests, because the glacial temperature, the surface temperature would be colder and entire profile would be colder. So, everything is shifted. So, you cool and you push the forest down. This is very relevant, because if we reconstruct the past vegetation in detail, what is very critical is that not all species can move. Some species just go extinct. Okay. Why is this relevant? Because in global warming, when we are either destroying forests or forests are being forced to move because of global warming, not the entire ecosystem moves, only few species move. So, they are something called mobile generalists, which can adapt quickly to changes in temperature and precipitation, and there are so called sedentary specialists, which do not move when things change. When environment changes, they are unable to move, so they just die. So, every time we are doing the reverse in global warming. So, in global warming, we are going the other way. We are increasing temperatures up the mountain. So, the vegetation is going up, mosquitoes are going up, diseases are going up, and so on, and the same thing in latitude. So, it is very critical to watch which species can move and which species go extinct. So, the entire ecosystem, what does an ecosystem mean? Basically, if you go outside and look where there is just wild vegetation, let us say you go up Panchavati in Pune or some forest nearby you, it consists of many species that have naturally evolved in that microclimate, and that is an ecosystem. Any given place, a set of species that are naturally occurring. When we do gardening and agriculture, obviously we change ecosystems, but the ecosystems that evolve naturally given a certain amount of light, temperature, precipitation, and so on, and what animals live there, what grazers live there, what birds are there, monkeys, etc. That ecosystem is in some sort of an equilibrium. When you change temperature, precipitation, and if they are forced to move because of the mountain temperatures or whatever, not all species can move together. That is something becomes very important. So, we could not learn all the details because we do not have all the details of the biodiversity or the species that were present in this forest, but we can use the model, look at the changes, and then try to see which species can move and which species cannot move. So, the causes of climate change during deglaciation, just to re-emphasize, we will look at a little bit more detail, especially in terms of how we give the information to models. So, remember, the models just need to know how much the radiation changed at the top, and if it's a full earth system model, then it can do the changes in glaciers, changes in carbon dioxide, methane, vegetation, everything. If it is not a model that has full vegetation, it will sometimes be given the changes in carbon dioxide and so on. So, there are all these kind of details which you don't have to worry about, but if you are interested, you can always dig more into it, and there are even ways to set up the simple earth system models so that students can play with them. Okay. So, here is the CO2 that was about 200 ppm when the last glacial maximum was coming to an end. It increased initially. So, this is the present level, this is compared to the present level. So, it increased here going from 200 to about 280 or so, and then agricultural society started. So, these scale is not showing the detail, but in a later profile I will show that actually the impact of agriculture begins to show here, and there is a small increase, and then industrial revolution there is a much bigger increase, and the ice decreased as we seen before, and the summer insolation kind of became above the threshold at some level, and it has come back, and here is the winter insolation. Okay, these are kind of the main forcings for, but remember that as the glacier begins to melt, all the feedbacks begin to happen. You have the ice albedo feedback, we are going in the melting phase. So, we have glacier decreasing, albedo decreasing, amount of energy absorbed increasing, which will accelerate the warming and hence the glacier melt. And you also have the vegetation feedbacks that we just looked at. Every time vegetation moves or changes, there are not only albedo changes, but there are also humidity changes and so on. So, we have to be always aware that even though we are showing simply as what are the forcings, the internal feedbacks determine the rate at which the changes actually happen. So, what was the retreat like in terms of the years, calendar year? So, you can see these are shown in C14, thousands of years of C14. So, 18 to 14,000 years ago, all these dark blue spots here, this is where the maximum extent of glacier was. There is also a thickness map associated with this, but that has quite a bit of uncertainty. So, I am not going to show that, but the extent could be easily much more accurately determined. Why? Now, you have to go back to your knowledge of what the evidences of glaciation are, like glacial striations, tillites, ice debris, and moraines, especially terminal moraines, and so on and so forth. Okay? And you can see that slowly 12,000 years, 10,000 years, 9,000 years, and so on, by 6,000 years you are all the way back here. So, the retreat of the ice occurred over these slow time scales, and there are some hiccups because as glaciers began to melt, they had scoured the earth here and created the so called Great Lakes, where the ice melted and occupied the soft land that had been carved out, and the melting didn't happen continuously because the meltwater, as we will see, was flowing south and flowing east, some of it flowing west, and there were issues that held the meltwater for a while and released them suddenly, and that has a certain feedback that relates to the meridional overturning circulation. Lot of really interesting feedbacks. So, we have to learn these because we are kind of seeing the reverse of these changes going into global warming. So, every feedback that is potentially there in the system must be understood so that we can keep an eye for what would happen in the reverse situation going forward and how the models can reproduce them and project them into the future. So, you expect that as the glacier melts, the sea level would go up naturally, right. If you have a glass of water and you have ice in it, the level is not going to rise because the ice water volume is already in it. But if you had an ice in your hand and you plunked it in, then that can change the level of water. So, the same way, if you have glacier on land, how did you build it? You basically kept on evaporating water from the ocean, put it as snow on land, and kept on putting more snow and compressed it into a glacier, which means you have essentially transported the water from the ocean and frozen it into the glacier. So, when the glacier melts, all that water is going to go back into the ocean and raise the sea level. What else is going to happen? As we said, when the glacier grows, it pushes down the land under it and pushes the land up ahead of it. So, if you think of it, all the land under this would have been pushed down, all the land ahead of it, all the way to Gulf of Mexico and so on, would have been pushed up. So, land pushed down here and ahead of it pushed up, and as this glacier melts, the land under it begins to rise and the land that was pushed up begins to sink. These are called post glacial rebounds. The land is rebounding. So, relatively speaking, the sea level will change. So, if this land is rising, relatively speaking, the sea level will drop here. If there is post glacial subsidence in front of it, the land is sinking, then relatively the sea level will rise. Why is this important? Basically because if you look at regions like New Orleans, where Hurricane Katrina hit and there was a lot of inundation, they are in a post glacial subsidence. So, sea level is already rising. Global warming is also increasing sea level because the water is expanding because of warming. So, if the sea level rise is much faster in those regions where land is sinking and global warming is increasing the sea level. So, those become, then when a storm comes, they become very vulnerable to the sea level inundation. There are other factors, of course. They would have removed mangroves and other things which would naturally damp the waves and damp the hurricane water and so on, just as we are doing in the Ganga and Brahmaputra delta, where we have removed a lot of the mangrove forests. We make the situation much worse with global warming. Okay, something to remember, but I am adding all these details in this chapter because these are the ones that we will keep coming back to under global warming. So, this is the sea level reconstruction, again time back to 1,000 years, and this is depth below modern sea level. So, if you look at all the glaciers that existed, how much water would you have removed from the ocean to freeze onto the land as glaciers? That amounts to about 120 meters. That is pretty significant. If the sea level drops by 120 meters, enormous amount of new shelf area would have opened up, and those are reconstructed using either C14 or thorium uranium ages. They are slightly different. C14, as you know, is produced constantly in the atmosphere. Once it is buried into organic matter or into the sediment, it begins to decay the isotope, and that tells us how the timing of the sea level change has happened. Uranium thorium or thorium uranium, you remember, is the rainwater that is seeping into the ground and dripping into speleothems, stalagmites, stalactites and so on. Uranium is soluble in water, thorium is not. Uranium decomposes into thorium, but thorium, unlike most other daughter product of the isotopic decay, is not stable. It itself also is radioactive, but the two reach an equilibrium when this uranium decays into thorium and leaves a signature in the water. So, that equilibrium is traced. The net result is that there are some differences in the estimated age of the C14 and uranium thorium. The differences are known, the uncertainties are known, but nonetheless it is very encouraging that they show similar behavior. But you can also see that the rate is not uniform. It kind of flattened here which we will come back to, and it accelerated over here. What causes those things? So we have to see that. So sea level also, like sea surface temperature, will not increase uniformly everywhere. So maybe we will see an example of the Indian Ocean, where the Indian Ocean sea level is not increasing everywhere. There are regions where it's actually decreasing. So that is something to keep in mind. If you are a coastal state like, let's say, Maldives or Fiji or Vanuatu or Andaman Nicobar, you should be aware of whether the sea level is expected to rise where you are or it's not going to rise. This is very critical, because a lot of planning, like some islands like Vanuatu are expected to sink, so they are planning to move the entire population somewhere else. That's a massive planning. So you have to be pretty sure that sea level is actually rising. If you are in an island where sea level is not rising, then you have to be sure that it's not going to rise, because you don't want to be caught by surprise. Sea level rises slowly anyway, but each time it rises, if there is a hurricane or a cyclone or a typhoon, it brings more water as the sea level continues to rise. So those will get into climate impacts, climate adaptation, which means how do you adapt to the coming changes. Those are all kind of the critical questions. So this is a chapter that I'm going a little bit slower, basically because we have many interesting feedbacks and responses in the system that are very relevant for global warming time scale. It's not that tectonic processes and orbital changes are not relevant, it's just that this hits home, closer to home, so we can learn a lot, and this is a period where we have relatively more observations. It's easier to run the models for this period and learn a lot. So we have a lot to learn also from the past, but this period, the more we learn, the better we will be in understanding what comes in the future with our continued human activity, or what are the critical points in the system where rapid growth can happen, and how do we tackle those, either by engineering approaches or by reducing our carbon emissions, and so on and so forth. So we will continue this discussion when we come back. So we'll see you next time.